Classical curves are really important because they're the types of equations that you could get, the types of graphs that you can get that aren't your ordinary function graphs just in polar form. These are ones where if you saw the rectangular equivalent of it, you'd say, well, there's no way I'm graphing that in a rectangular coordinate system. That's kind of the idea, is that we can now graph things that look like this, and if you think about it, like how on earth that rows, how on earth would you graph that in an XY coordinate system, in a rectangular coordinate system? It's not even a function. You'd need to do it as a piecewise function, and there would be a lot of pieces to it, right? So the idea here is that we're able to, hopefully, with relative ease, come up with the graphs of these types of equations. So for now, we're going to go with a table of values approach. And once you get the hang of it, you start seeing what little shortcuts there are and so on. So let's make a table. We got an R and a theta. That R is dependent on theta. So I'm going to start off, my first column is going to involve the thetas. All right. I'm going to actually put the expression in there so I can have a place of substitute. 3 plus 3 cosine theta, which would, after completing that computation, give us an R. All right, so then the big question would be, well, what theta values? But if you think back to when you make a table of values for a parabola, you'd have the same question. All right, what x values do I use? Well, where's the parabola? Well, if I knew that, I wouldn't have to graph it. So what do? You usually pick a representative set of x values. You try to get 0 in there because 0 is a nice convenient value. Some nice numbers that are nice relative to the equation that you're working with. So if you had something like 1/2 x squared, you'd probably want to choose values of x that would lead to even numbers, so it's easy to divide it out. It's the same idea here, except we're obviously working with angular measures, right? Now it's up to you if you want to work with the radians or degrees, but I can tell you that eventually, for some situations, you're going to be forced to work with radians, and in other situations, you're going to have to work with degrees. So you got to be able to be flexible enough to work back and forth between the two. So don't fall in love with one over the other. In previous classes, it was, all right, we're doing radians and that's it, or we're doing degrees and that's it. Now it's like, well, we're going to do radians this time, and sometimes we're going to do degrees, right? So here I'm going to I'll do radians, right? Because I feel like, if I'm doing the example, radians make more sense because at least I'm guiding you through it. But like I said, 0 is a good number to get involved in the action, right? So 3 plus 3 times the cosine of 0, and that's 0 radians. All right. So as long as you know or can figure out or have access to what the cosine of 0 is, you're in good shape. All right, so cosine of 0 is equal to 1. 3 plus 3 times 1 is going to be equal to 6. All right, now the thing that makes this probably more confusing than it ought to be is the fact that we plot ordered pairs for polar graphs as r comma theta. So this is, again, r comma theta, 6 comma 0. All right, so normally, if you're doing XY coordinate system, you get an X value, a Y value, and then it's X comma Y. So here you get a theta value and R value, but then you switch them in order to come up with the ordered pair, right? But then, to make it even more complicated, we still identify the location of the theta value on the graph and then take R steps in that direction, right? So 1, 2, 3, 4, 5, 6. So I'm kind of off the grid here, but the point would be roughly about right here. All right, 6 steps in the direction of R. All right, so we got a point. So now what I want to be thinking about, because I can go the next one if I want, I can do pi over 12 and pi over 6 and so on. But what I want to be thinking about at least to get the ball rolling here, would be values of theta that are convenient for the cosine function, right? So, and that requires a good, solid understanding of the unit circle, right? So we want values of theta, and we may have to settle for other values of theta, the ones that are not convenient, if after we plot all these points, we still don't have an idea of what the graph looks like. But if this is enough, if we can get some good values for theta to make our lives a little easier, then that's going to be the way to go. So that are cosine friendly. All right. So, you know, you don't have to write this down, but if you have no idea, then maybe you do. Anything that's a quadrantal angle, so anything that falls on an axis, is going to be cosine friendly. So quadrantals. All right, so that's your poor quality squiggly bracket. 0, pi over 2, pi, 3 pi over 2, and so on. And then also 60-degree reference angles. All right, so that's your pi over 3, 2 pi over 3. I could say 3 pi over 3, but we already got that. That's pi. 4 pi over 3, and so on. Yeah, because those are the ones that are going to give you, you know, you think about cosine 60 degrees, that's equal to 1/2. So that's going to give you some type of 1/2, whether it's positive or negative. Those are the ones you kind of want to steer towards. But you could also pop this stuff in the calculator and be done with it. But if you want to have a good sense of how things work and why things work, this is the way to do it. So looking at my array of values here, the next one that I would select after 0 would be pi over 3. So 3 plus 3 times the cosine of pi over 3. So 3 plus 3 times 1/2. So 3 plus 3/2, that's going to be 3 plus 1.5, which is 4.5. All right. Your best bet is to put that either as a mixed number or a decimal, because we got to plot them anyway. So I'm going to put it as a decimal. 4.5 as the radius, pi over 3 as the angle. All right. So then I would identify pi over 3 on my graph, and I would take 4.5 steps towards pi over 3. 1, 2, 3, 4, and 1/2. I got a second point. Yeah, this is working out nicely. All right, next up would be pi over 2. And you could use the circle, you know, the labeled circle as a guide, because maybe you're like, I don't know what comes next, but you look at your list of possibilities and say, okay, pi over 2 is, as I work my way around, is the next one that would come up. So that's hopefully a good strategy. So pi over 2, 3 plus 3 cosine pi over 2. Anything on the y-axis, if you think back to the ordinary unit circle, the x value of the coordinates on the y-axis are always 0. Cosine is the x value, and so therefore cosine on the y-axis is always going to be equal to 0. So this just ends up being equal to 3. So 3 comma pi over 2. So 3 steps in the direction of pi over 2. And we're looking at 2 pi over 3. Now I'm showing a lot of work here for something that you probably, a lot of you would not need to show a lot of work for, because if you know your unit circle, you're doing a lot of this in your head. And if you don't know your unit circle, you're probably doing a lot of this in the calculator. So, you know, just bear with me here, because I'm doing this for note-taking purposes, but also because I do have a lot of experience with this course, and I know that the biggest weakness that people have coming into this class is their knowledge of trigonometry, right? That being said, same reference angle, so 2 pi over 3, pi over 3, 4 pi over 3, etc. They're all going to be some kind of 1/2. So it's just a question of what kind. Is it going to be positive or negative? In this case, it's going to be negative because we're in the second quadrant, right? When you're in the second quadrant, the cosine function is negative. So we're looking at 3 instead of plus 3/2, it's going to be 3 minus 3/2. So 1.5. And so this ends up being an ordered pair of 1.5 comma 2 pi over 3. And also, because I took the time to select clean values for cosine, and you know, there is a part where you actually have to have a little bit of, or you have to have enough sense to know what's a clean value and what isn't. But because I had enough foresight to choose clean values, what I'm looking at are clean results for R. So if you take the time, even if you know your unit circle, you just don't want to do the mental gymnastics to come up with these answers. You could say, well, I'm choosing the best possible values for cosine so that when I put it in my calculator, I'm going to get 6, 4.5, 3, 1.5. I don't have to jump through too many hoops. All right. So then next up would be pi. Three plus 3 cosine of pi. Cosine of pi is equal to -1. So 3 minus 3 is 0. So we're looking at 0 comma pi. But 0 comma anything is putting you right smack dab at the pole. All right. Now, since I know this is going to be a smooth curve, I can actually start drawing this a little bit. You could also use the table above to kind of guide your thinking and what it ought to look like. But for now, I'm just going to say we'll plot a few more points so we can verify. But we're looking at something like that. I could probably have done a better job on that last bit. It looks pretty much exactly the same. I'm going to live with it. So we got that part. Now I just need any other parts that might exist. Now, they did not give us a domain here. If they did, we would have known what theta values to use. But they didn't give us a domain, which means that we got to keep going until we close the loop. You can see in all the cases above, all those general graphs, that they're all closed loops, except for the spiral of Archimedes. So we got to keep going. But if you look at the one that models this type of equation, the case of the cardioid, you can see that it is symmetric about the x-axis. So you could probably jump to the final answer right away, but I'm going to say, we'll sit tight. All right. So next up would be 4 pi over 3. So 3 plus 3 cosine of 4 pi over 3. Third quadrant where cosine is negative. All right, so it's another one of those 3 minus situations. Cosine 4 pi over 3 is -1/2. 3 times -1/2 is -3/2. 3 minus 3/2 is 1.5, or if you want 3/2. All right, so my little alignment scheme here is getting a little out of whack, so let me do that. So we're looking at 1.5 comma 4 pi over 3. So 1.5 steps in the direction of 4 pi over 3. So I need 4 pi over 3, and then I'm looking for 1.5 steps in that direction. So right about, yeah. So we could already see that the symmetry is shaping up the way that we suspected it would, because this is definitely symmetrical to the top half. All right, next up would be 3 pi over 2. So 3 plus 3 cosine 3 pi over 2. 3 pi over 2 falls on the y-axis. Cosine on the y-axis is equal to 0, so 3 plus 0 is 0. All right, so we're looking at 0, comma, 3 pi over 2. Our value of 0 means we're plotting at the pole, but I already have that point, so I don't need it again.
Why is that 0 and not 3?
It should be 3. Thank you. And so it wouldn't plot to the pole. It'd be 3 steps in the direction, 3 pi over 2. The case of me wanting the answer to be one thing when it really was something else.
Should plus 3 cosine pi be 3, not 0?
Which one? Sorry.
When theta is a pi.
Oh,
So,
for pi?
Yeah.
Well, that one's going to be 3 minus 3. So that one should be 0.
Thanks.
Cleaning up a little bit. All right, so then next up, if I'm not mistaken, 5 pi over 3. And then after that, we should be able to close the loop. 3 plus 3 cosine 5 pi over 3. Fourth quadrant, cosine's positive. Right? So 3 times 1/2, 3 halves, also known as 1.5, added to the 3, and I get 4.5. All right, so smidge that up. We're looking at 4.5, comma, 5 pi over 3. All right, so that's going to be 4.5 steps in the direction. 1, 2, 3, 4.5 steps in the direction of 5 pi over 3. The only challenge, I guess, at this point is not going cross-eyed when you're counting up all these little markings. But now I can just close the loop because the next one is going to be at 2 pi. And 2 pi should, well, 2 pi is at the same location as 0. So that'll bring us back to the same spot. All right. And so that's what our figure ought to look like. And that is the case of the cardioid. Now, in terms of the name of the classical curve, is it a big deal if you don't know the name? Not a big deal. It just helps, you know, so that when I use the terminology, it makes a little bit more sense. But there's no reason why you can't just refer to this page, right? The remaining problems, they're all going to kind of follow the same idea. So I don't want to waste too much of your time by going over these point by point. So what I'll do is I'll put a star on the next one. And on the next page, what I'll do next time after we go over number 12. So I'll start off class going over number 12. So you'll try that one on your own, and then I'll go over it next class. Then I'll show you the shortcuts for 13, 14, and 15, right? Because there are shortcuts. It does involve some memorization, but it's one of those things. It's kind of like if you've ever taken a stat class, you don't know to appreciate the fact that the calculator computes standard deviation for you, for example, until you've had to compute it by hand a couple of times. And then you're like, oh, if only there was an easier way, right? So I'm only going to make you do it the long drawn out way once on your own. And then after that, I'll show you the shortcut, and then you can decide which way you like more, all right? So that is what I offer you this evening. So let me stop that recording. And now we're going to talk about derivatives.